A weak base is a base that doesn't fully dissociate or react in water. Examples are ammonia, ammonium hydroxide, water, or the conjugate base of a weak acid. For example, CH3COOH is acetic acid. This is a weak acid, and so its conjugate base, CH3COO- or acetate, is a weak base. In our example here, we're asked for the pH of a 3 molar solution of acetate anion at 25 degrees Celsius, and we're given the Ka value for the conjugate acid of acetate, which is acetic acid. The first step here would be to recognize that we have a weak base. We could know that this is a weak base just based on the information in the question because we're told the Ka value for the conjugate acid, and this Ka value is much less than 1, so we know acetic acid is a weak acid, and thus its conjugate base is a weak base. We're told that we're in a 3 molar solution, which we assume is an aqueous solution, so when we write out the reaction here, this will be for acetate in water. So I'll write out the reaction now. This is our reaction, and we now need to complete an ICE table, which is initial, change, and equilibrium values for each chemical in our equilibrium reaction. We can ignore water since it's a pure liquid and won't affect the values of our equilibrium expressions later on. So we will start by putting in the initial amount of acetate anion, and we'll assume that we start with no products. We know that this is a weak base, which means in the change row, we can put that we have a very small amount reacting minus X, X representing an unknown small amount. So at equilibrium, we have 3.0 minus X molar. On the product side, we will be gaining X, and thus at equilibrium, we will have X molar of each of these species. Notice that X molar is going to be giving us the concentration of hydroxide. So what we'll want to be doing next is solving for X, since once we have the concentration of hydroxide, we'll be able to calculate the pH and solve this question. To solve for X, we need to use another expression. We could use the equilibrium expression for this reaction, or the Kb expression. So Kb is the concentration of products over reactants. Notice that I have left out water since it is a pure liquid and its concentration is not included in the equilibrium expression. I will now fill in the equilibrium concentrations of each of these values. So from the table, we have X and X for the product concentrations and 3 minus X for the reactant concentration. To simplify this expression, we're now going to assume that X is small, so that 3 minus X is essentially still just 3. Our next step is to get the value of Kb. We weren't given the value in the problem. Instead, we were given the value of the Ka of its conjugate acid. We know that Kw, which is the autoionization constant for water, is equal to the conjugate acid equilibrium constant multiplied by Kb for its conjugate base. So we can solve for Kb as equal to Kw divided by Ka, or we could also call this Kw times Ka to the minus 1. So I'm going to solve that in over here. So we'll say that this here is x squared over 3.0, our Kb, is also equal to Kw times Ka to the minus 1, and I will solve for x here. So x is equal then to the square root of 3.0 multiplied by Kw. We can fill in that value, which is 1.0 times 10 to the negative 14. This is just a constant at 25 degrees Celsius, and the Ka is given in the question, 1.77 times 10 to the negative 5. This value here is 4.1169 times 10 to the negative 5, and I'm going to put in the units of molar. This is our concentration of OH minus at equilibrium. It is also the concentration of acetic acid at equilibrium, but I'm not being focused on that one since it's not going to tell us about the pH. So our pH is equal to 14 minus POH, and that is equal to 14 minus the negative log of the concentration of OH minus. So I can fill in that value here. So 14 minus the negative log of 4.1169 times 10 to the negative 5. And that gives us our final pH of 9.61. We should go back and double check our assumption that x was small was a valid assumption. If we look at our value for x, we can see it's on the order of 10 to the minus 5, which is indeed much, much smaller than 3. And so this was a fine assumption in this case.